So 6 is about exponential and logarithmic equations. So we've learned how to manipulate them so that we could learn how to solve equations that contain those things. Okay, that's the main goal, is getting to 6. So all the rules we have learned so far we can use, but one of the most powerful rules is the one-to-one property for exponential functions that basically says, if we can get the bases to match, we can ignore them and just set the powers equal to each other. And so it makes a complicated equation that looks like this become much simpler because we can ignore the bases. We can cross out the bases if they match and just solve the equation by making the powers equal. And look how much easier that becomes. That becomes a very simple equation. And you just solve it, okay? So we're going to get, we need the x's to one side, numbers to the other. Let's subtract x from both sides. Let's add 4. So x will equal 3. Now, exponential equations have infinite solutions. There's nothing that messes them up. So we don't necessarily have to worry about something that won't work. Whatever answer we have is going to be the answer that's going to work. So you'll notice what I did. If the bases match, we drop them away. We just set the powers equal to each other, and we solve it like a normal, good old equation. Get the x's to one side, numbers to the other. That's your answer. Exponential equations, when you get the powers to match, are easy. If we can't get those, or if we get the bases to match, is easy. If we can't get the bases to match, it's not as easy. But I'll show you how to fix that as well. Okay, so that's our first one. Let's look at this one. Now, the last one, it was very obvious that the bases match. This one is not as obvious, but hopefully you recognize that 8 is a power of 2, and so is 16. So usually what you're going to do is you're going to take the numbers and you're going to break them down so that they have a common base. So hopefully you recognize that 8 is 2 to the third. Now, take off that 8, replace it with the 2 to the third. Whatever power was there, put it in parentheses. Okay, take off the 8, replace it with a 2 to the third power, and then whatever power is there, put it in parentheses. We're going to do the exact same thing with the 16. If you calculate 16, it's 2 times 2 times 2 times 2. It's 2 to the fourth. So we're going to take off the 16, replace it with a 2 to the fourth, and put the original power in parentheses. Now we have a problem exactly like example 1. The bases match, so we can cross them out. So we just get 3 times the quantity of x plus 2 equals 4 times the quantity of x plus 1. Much nicer than what we started with. Okay, so if you can get the bases to match, that is the key. Get the bases to match, and that's the key. So usually you're going to break down larger numbers to their smaller components. Okay, now here to solve it, it's pretty straightforward. We distribute both sides, and then we just get the x's to one side, numbers to the other. So if I subtract 3x's from both sides, and then I subtract 4 from both sides. There you go, okay? And you can check in the original. If you plug 2 into the original, that would be 8 to the fourth power will be the same as 16 to the third power, okay? So that's kind of how it works like that, okay? So if you can drop down the bases to be that smaller number, that's what you want to do. Now, sometimes it's not so obvious how we can get them to match. But let's think about it for a moment. We have learned and we've discussed and when we first even were graphing square roots, that is the same as a 1/2 power. And you've noticed that we have been rewriting square roots with that 1/2 power again and again. And that's going to be super important that we are able to do that. Because as soon as we got the bases to match, and we see those powers, you can cross off those bases, and it's just 5x equals 1/2. Now, what you can do to make it a little bit easier to solve, per se, I think you can think about it as dividing by 5 or multiplying by 1/5. However you want to think about it, it should work out that x is 1/10. Now, another way to think about it is if I'm multiplying here, when I divide on the other side, I cross over and multiply. So that's why we get 1/10. Okay, so you can also think about it as 5x over 1, take the 5, cross multiply. So that will also be a way to think about it. But however we do it, we would get an answer of 1/10. And let's think about if we stuck 1/10 right here, 5/10 is a half. So they would both be equal to a square root of 2. So if you have something inside a radical, always get in the habit of making it a fractional exponent, okay, with our rules of fractional exponents. Everybody good with example 3? Okay. Now, here's one that's kind of interesting. If you think about the way that powers work, there is nothing we can put on a 3 to turn it into a negative. This is always a positive quantity. This is always a negative quantity. They will never be equal. So this one is a no solution. There is no way I can put anything on a 3 to turn it into a negative. Now, if both sides are negative, yeah, you can divide the negatives off and go about your business. But if one side is positive, one side is negative, there's no way for us to deal with that. Powers do not change the front sign of something unless there's some kind of parenthesis with a negative in it, which we don't have on that left side. So that's really saying that a positive is equal to a negative, which is not true. So you just throw it out and go, can't solve that one, okay? Now, here's one of our more difficult types. There is no way to break down the number 5 and the number 4 to make them match. 5 is a prime number. 4 is 2 times 2. They have nothing in common. So we can't do the trick we did with example 1, 2, and 3. We just can't. So here we have to do a more difficult trick. So this is one of the hardest ones we're going to do. You're going to stick a natural log on both sides. Now, I always use a natural log just because it's easy to write. That ln's quick and easy to write. I can use a calculator if I need a decimal value. You can use log, you can use ln. I don't know. I just always use ln. Okay. Now, the reason we do that is so we can use a rule we learned last week. We can take our powers, if there's more than one term, put it in parentheses, and we can drop it down in front. Okay, so our goal here is to free the x's from the powers. Now, if the bases match, that's how we free it. We can just cross out those bases. If the bases never match, okay. So this is what we're going to do. We're going to drop that x plus 2 down in front. We're going to drop this x down in front, okay? Now, let's just think for a moment. The natural log of 5 is some number 1 point something. The natural log of 4 is a different number 1 point something. I don't know what it is, don't care. Think of it, it's a number. This represents a number, this represents a number. If I had an equation that said x plus 2 times 3 equals x times 7, whatever, you would distribute, right, to get to the x's. Same thing here. Next thing we're going to do is we're going to distribute. So this is x times the natural log of 5 plus 2 times the natural log of 5 is x times the natural log of 4. Now, here's what we're going to do. You always kind of do this in stages. We drop the powers, distribute, and then we're going to get the x's to one side and the numbers to the other. So this contains an x and this contains an x. Those pieces are going to go to the left. The piece that doesn't have an x is going to go to the right, okay? So we're going to get x natural log of 5 minus x natural log of 4 equals -2 natural log of 5. So all I did was bring this one over here because it had an x, and bring this one over here because it did not. When it moves, it changes sign because I'm subtracting it. Everybody with me there? Okay. Now, in mathematics, if things are not like terms, we cannot add them. It's just we can't. Okay. These are not like terms. We can't add them. But we can do a trick. They both have an x in common. I can factor. So when I can't add, I can factor. Let me make that look better. So what I'm going to do is I am going to factor out the x that they both contained, because my goal is to make this equation say x equals all the other junk, just like any other equation. Now, x is multiplied by that junk in the parentheses. So for us to solve for x, we just need to divide both sides by that junk that's in the parentheses. So now it always becomes the same thing. It's the left or the right side divided by the parentheses that was on the right. You cannot simplify that. I don't want it from a calculator. I'm not going to waste your time entering that into a calculator. I know you know how to enter that into a calculator. So that is the exact answer. I want that answer. I don't want anything more than that answer. Leave it, leave it, leave it. Okay, so let's go over the process one more time. Any factors or, powers that have more than one term, put them in parentheses. Drop them down in front. Distribute if you need to. Get the x's on one side, the non-x's to the other side. Factor out an x. Whatever's in parentheses, you divide off. Now, in calculus right now, we are doing a type of derivative called implicit differentiation. It's a complicated word, but we use almost the exact same technique there. If they're unlike terms and you can't add them, you factor out what you want, you divide off the other piece. That's always the order these ones go in. And they're hard, they're gross, they're disgusting. I know. Okay. So that's one of the hardest types. This next one looks difficult, but it's not. If one side has a power on it, one side doesn't, your goal is to get the thing with the power by itself, okay? So let's get rid of this 20. Let's divide both sides by 20. So we're going to divide both sides by 20, and I think it should be a 2t power. Anyway, we're going to divide both sides by 20 so that we can get that e to the t all by itself. Okay. So 100 divided by 20 is 5. Now here's where what we learned last week is going to really come and help us. We learned that the log base b of a number equals the power. And we could switch that at any time to say that the number is the base b to a power. Those things are equivalent. So we are allowed to take an exponential and we are allowed to turn it into its logarithmic opposite. You know, it's equivalent. So we can take this and then turn it into a logarithm. So what's the base for what kind of logarithm would we want for an e? Well, we want a natural log. So what's really cool is if you stick a natural log in front of both sides, when your problem contains an e, it fixes the issue for you. Or when one side contains an e and one side doesn't, just stick a natural log on both sides and it will fix the problem. Because this is just a number. It's just the natural log of 5. This, we learned last week, the natural log and the e are opposites. They cancel each other out. That's just equal to 2t. So now we know how to solve for t. If t is multiplied by 2, in the past, we would just divide both sides by 2. Same thing happens here. We're going to divide by 2. And we get that t is equal to the natural log of 5 divided by 2. That's your exact answer. I don't want a decimal in your calculator. Don't waste the time entering it. That's exactly what t is equal to, the natural log of 5 over 2. So if you have an e in the problem, use a natural log to cancel some stuff out. Use the natural log to cancel some stuff out, and things will work out nicely, okay? So our last type of exponential is example 8. So we're skipping 7. We're going to jump to 8. Now you'll notice for example 8 that we have an e that has a double power and an e that has a single x power and then no e at all. That is one that is acting kind of like a quadratic. So we're going to set that equal to 0 by moving the 56 to the other side. And then we're going to use a technique called U substitution. Now, what U substitution does is it makes a more complicated problem start to look a little easier, okay? And we're going to make U equal this middle term, okay? So U is equal to e to the x. So U squared is e to the 2x. So we have something a little simpler to plop into our equation. So we get U squared minus U minus 56 equals 0. Now, if I ask you to solve that, I bet you most of you could do it. It's just a quadratic that is easiest to solve by factoring, or you could use the quadratic formula. So let's pretend like what you see here in red is what we were given. So let's pretend that's U minus 8 and U plus 7. Why 7 and 8? Well, 7 times 8 is 56. They have a difference of the -1 we want in the center. The negative goes on the 8 so that we get a -1 in the center instead of a +1 in the center, okay? Now, that gives us that U minus 8 equals 0 and U plus 7 equals 0. So U equals 8 or U equals -7. Now, we weren't solving for U. We were solving for x. So now you got to put back in what you originally substituted. So let's look what we substituted. U is equal to e to the x. So at this point, where the U is, take it out and put an e to the x. Now, if e to the x equals a positive number, that's the one we're going to solve. If e to the x end up equal in a negative number, just cross that one out. Because just like the problem we did in example 4, we can't have it equal a negative number. There's nothing we can do to turn that into a negative. But e to the x is something that's very easy to solve. X would be the natural log of 8. Why is that? Because an e to the x on the left is equivalent to a natural log on the right. E to the x and natural logs are flip-flops, opposites of one another. So that's a really nice thing to solve. I don't want a decimal value again. Leave it at natural log of 8. It is what it is. So that is one that's kind of an interesting type of problem. And then that leads us to the first homework, 6.6a. Okay. Now 6.6a, you don't have a lot there. You have 9 problems, okay? But I would like to do number 11 with you. So if you want to write this down with your notes, or just, we'll write number 11 down, and then we're going to jump to the second part of our lesson. Now, remember I said the key to exponentials to solve them is if we can get the bases to match. So some rules. If the bases are alike and we're multiplying, we get to keep the base and add the exponents. So we can just add those exponents up. Here, this is just 10 to the -1 because it's the reciprocal, and we flipped it, you know. And guess what? As soon as the bases match and it's base equals, or base to a power equals base to a power, we get to cross those off. And then it just becomes the simple equation, -2x equals -1. So x is 1/2. That's it, okay? The key to this homework is to get the bases to match when you can. And so that is number 11 from that homework. So now you only have 8 problems to do, okay? So 9, 10, 11, and 12 are very similar types to the number 11. That's why I wanted to do that. Okay. So now we're going to jump to the second part of the 6-6, which is about solving logarithms. Yes. Just like if we get the bases to match, we can drop things off. Here, we're going to use the switch between logarithms and exponentials that we have talked about in the past to solve them. So let's look at example 9, okay? Anytime you have just one piece in an equation that contains a logarithm, we want that piece alone first. So that piece needs to be alone first. How to get it alone? Well, let's just subtract 3 from both sides, leaving us 2 natural log of x equals 4. Now, we not only want it alone if something's added or subtracted to it, we want it alone if there's a number in front. So we do want to get rid of that 2. We want to divide both sides by 2. So if we divide both sides by 2, we get that the natural log of x equals 2, okay? We get that the natural log of x equals 2. Now, this becomes just something to switch. A natural log is an e. So if there's a natural log on the left, put an e on the right. So x is e squared. There's a natural log on the left, put an e on the right. X is going to be e squared. And why does it work like that? Well, if I put an e squared into that natural log, I'm going to get 2, because the natural log and the e squared would just cancel out and just leave me a 2. 2 times 2 is 4, plus 3 is 7. I get a correct solution, okay? So those ones are pretty nice. Now, let's do it again. We have a 6x in there, so we do have a little difference in example 10, but I did want you to see one like this. We're going to divide both sides by 2. We're going to just leave it. Let's just leave it 7 over 2. Fractions, as long as they're reduced. Yeah, go ahead. Fractions, as long as they can reduce, are fine. Or, you know, as long as they can't reduce, just leave them like that. If you can reduce it, reduce it. What's going to get rid of the natural log on the left? Yeah, just grab one of those. Yeah. It's going to become an e on the right. So it's just going to be 6x equals e to a power of 7 over 2. Now, e to the 7 over 2 is just a key number of some sort. I have no idea what it is. I could probably guesstimate. It's somewhere probably close to 30. I don't know, but who cares? It's just a number. If I said that 6x equals 12, how would you solve for x? You divide by 6. Well, this is still the same thing. 6x equals a number. To get rid of the 6, divide by 6. So we're going to divide both sides by 6. Now, we can't really write it much nicer than that. So just leave it e to the 7/2 power over 6. I don't know what it is. That's the exact answer. All I want on the homework are exact answers, unless it specifies to put it into a calculator and give you a decimal to so many places, and you would use a calculator. So that's example 10. Example 11, I'm just going to do, it's going to be a one-step, super quick problem. It's just x equals e cubed. If you didn't write that one down, I just want to show you how quickly you can solve it. If it says the natural log of x equals a number, it's just e to that number. Bam, you're done. Okay. So I did want to show you that quick little example. Okay. Now, a property that we can use that's really nice. Do you see how if they get everything inside of a logarithm equals to everything inside of the logarithm, they can knock the logarithms off and it's just the inside stuff? That is super great. because it makes a problem like example 12 that looks disgusting solve very quickly. See how it's the natural log of everything equals the natural log of everything? When that's the case, just like when we can cross off the bases, we can cross off the logarithms. So it just comes down and it's x squared equals 2x plus 3. Now that only works, it has to be the entire side. So that's where our rules of condensing, if we can condense it into one logarithm on the left side, condense it into one logarithm on the right side, take the logs off. We don't need them anymore. And that's why we learned those rules of condensing. Now, how do you solve a problem like that? Well, that's a quadratic. We've learned how to solve problems like that, get it set equal to 0, and either use the quadratic formula or try to factor it. That's factorable, x minus 3 and x plus 1. So x equals 3 or x equals negative 1. Now, here is where the problems that come up with natural logs become a problem. You have to check them. If you don't check them, you could get it wrong. Even though your math looks perfectly right, you could get what's called an erroneous solution. So we have to check because we can't put negatives inside of a logarithm. Let's make sure that when we plug in 3 on both sides, we get a positive. Well, 3 squared is 9. 2 times 3 is 6 plus 3 is 9. 9 equals 9. Bam. 3 is good. But now let's plug in negative 1. When we square a negative 1, it does become a positive, so the left is still good. When we plug negative 1 right here, we get 2 times negative 1 is negative 2 plus 3 is also 1. Oh, they both work. But don't expect that they will. Sometimes they do, sometimes they don't. Always check in your original. When you plop them in, they not only should be true on both sides, but they should be positives on both sides, okay? So we just have one last example. One last example is a half-life formula. Now, the formula is up on the board, but let's just talk about what each piece stands for. The A sub 0 right here is like our P in other formulas. It's the initial amount. This half is showing here because we've been given information about how long it takes for half of something to decay. That's used in carbon dating. If you're if you're taking a bone sample and you want to know how old that bone is, carbon dating, they do it. Uranium. So that is the formula we're going to use. It's kind of an interesting formula. It is used in a lot of scientific applications. Okay, so let's take a look at this problem, which is much better than what I wrote on the board, but it says, how long will it take for 10% of a 100-gram sample of uranium-235 to decay? So what you need to know is that formula, which you have written down, I believe, but I'm going to write it down for our purposes. You need the half-life time frame, and it takes 703,800,000 years for half of a sample of uranium to decay. We are looking for the T that it will take for our amount to be 10% of our original. Well, 10% of anything, you just multiply by 0.10, and 10% of 1,000 is 100. So we know everything we want. We started out with 1,000, that goes here. We now have only 100, that goes here. Wait, I have them totally mixed up, I'm so sorry. Wait, we started out with 1,000, that goes here. We want to have 100 left, that goes there. We don't know that, but we do know this, 703,800,000. Okay, so we have everything in our formula except for the T. Now, when our power is the thing that is stuck, when our power is the thing that is stuck. We're going to use logarithms to help us. Okay, we have to have the 1,000 gone. You can't have that 1,000 sitting there. So we're going to divide both sides by 1,000. Well, 10 divided by 1,000, guess what? Amazingly, it's 1/10 or 10%. Now, when I said if we can't get the bases to match, well, we can't make 1/10 turn into 2's. When we can't do that, we have to use a natural log. So just stick a natural log on both sides. You just stick a natural log on both sides. And the reason we do that is so we can drop the power down in front. So we're going to be able now to drop the power down in front. So we get the natural log of 1/10 equals t over 703, 800. You got it, you know what I mean, times the natural log of 1/2. Okay. Now, at this point, let's think about how to get t by itself. It's just an equation now. The t is multiplied by the natural log of 1/2. So what gets rid of a multiplication but to divide? It's dividing by 703,800,000. So what's going to get rid of that but to multiply? Okay, so what's our answer? Well, t is going to equal the natural log of 1/10 divided by the natural log of 1/2 times 703,800,000. Now, it's a real life application, so put it into a calculator, round to the nearest, let's go 1/10 of a year, okay? So if I put into the calculator the natural log of 1/10 divided by the natural log of 1/2, watch your parentheses, times 703,800,000, I get that for only 1/10 to remain, look at how many years it's going to take. I'm going to just it takes 2,337,972,993 years for 1/10 of it to remain. Now, the reason it takes that long is because for 1/2 of it to remain is that 703 million years. And so it should, 1/10 is a lot less than 1/2. And so it makes sense that it's such a giant number. And that's the problem with nuclear waste and things of that sort. That's the type of uranium that's in like nuclear weapons, and I think even in like power plants. And so, you know, the Chernobyl, all those things, look how many years it's going to take for just 1/10 of the materials to be gone. We're not going to be around then. So here's some equations for you to solve. Now let's talk about this week, because unfortunately it is what it is. This week, we did this today. Tomorrow, you're going to have class time, and you're going to have a chapter 6 review that reviews everything. And it's a video, and you can watch it. It's there now. You can watch it if you don't have anything going on tonight. You could watch it tonight. And then there's a take-home test that's due by Thursday at midnight. It is worth a test, and you may use whatever resources you need to get this test done, but you must show your work. Okay, so every problem you're going to take a picture and you're going to submit it. It's going to be in a Google form. But, you know, take a look at all the chapter 6 stuff that was due yesterday. Did you turn it in? These 2 homeworks are due. There is a review due, and there is the chapter test due this week. Tomorrow, I'll give you the password to open up the test. The test is sitting there, but you'll need a password to open it up, so I'll give you that tomorrow. But there you go. And you still have a little bit of time if you want to, try some of these problems, or I can put up here so you can look at some of those if you want to give them a shot. But there you go.